Okay, this is a talk about cosmic rays. We'll be having a look at cosmic rays literally in the sense that we will be seeing them, but I'll be giving you a little bit of background. And before talking explicitly about cosmic rays, I want to make sure everybody understands the concept of radiation. So I'll be talking about background radiation and radiation from the Earth before talking about cosmic rays, looking at a little bit of history as to how we discovered cosmic rays 100 or so years ago and what we understand about them now. I'll be talking about how we detect cosmic rays. We have a couple of detectors here on the bench in front of us. And I'll finish by asking, where do cosmic rays come from? In other words, what are the sources of the particles that we're seeing here on Earth? And then I'll sum up at the end. So the MCAG lawyers insist that I say this. There are some tabletop demonstrations here, and there are some radioactive samples. None of this is a problem for you. The radiation from these samples basically doesn't go more than centimeters. In other words, as long as you keep your distance, you're quite safe. At the end of the talk, I'll take the radioactive samples and I'll put them away so you're free to approach the bench and have a closer look at the tabletop demos if you so wish. So what I've got on the front bench here is a Geiger counter, and I've got a cloud chamber, and it's the cloud chamber that you've been watching for the last half hour or so, showing us cosmic rays going through. So let me just put the speaker of the Geiger counter back on again. I presume you can hear the clicks okay. Yep. So the question is, what is it that's doing the clicking? Well, each click basically signals the arrival of a subatomic particle, arriving at what everybody calls a Geiger counter. Now, physicists rather don't like this, because it really should be called a Geiger-Müller tube, because those are the inventors of this particular technology, Geiger and Müller. But everybody seems to call it a Geiger counter, so we won't be too pedantic, we'll just stick with calling it a Geiger counter, even though that's not quite the right name for it. But a Geiger counter does what it says, at least, and that is, it just counts clicks. It basically tells you how many clicks per second or how many clicks per minute. What is each click? Well, each click is a subatomic particle. Where did they come from? Well, maybe the subatomic particle that we're hearing on those clicks, maybe it came from an atom floating around in this room. But it's also quite possible that each click that you're listening to actually started its life a lot more distant. It might have started its life in a supernova that went off perhaps in a galaxy a long time ago, in a galaxy far, far away. The bottom line is a Geiger counter can't tell us. A Geiger counter just tells us how many things are passing through the detector. The Geiger counter doesn't, in a sense, discriminate. It could be electrons, it could be other particles, which we'll come to in due course. We'll need a different type of detector if we want to tell the difference between the different types. Geiger counters just tell us how many are coming through. So the clicks are going to get irritating, so I'll just switch the speaker off. So the Geiger counter will continue, but the speaker will be muted. So let's have a think about background radiation before we get stuck into cosmic rays. We'll be looking at terrestrial radioactivity, and I'll explain what I mean by different isotopes of different atoms. So radiation is around us all the time. Some people think that radiation is a bit of a scary word, but bear in mind that you've lived with radiation all of your life. And so we're just going to have a think, before we talk about cosmic rays, about this background radiation. We have to remember that the Earth is radioactive. This is nothing to do with mankind letting off A-bombs, which unfortunately we did back in the 60s. The Earth is radioactive because the Earth has always been radioactive. Ever since it was made 4.54 billion years ago, the Earth has been a radioactive rock spinning in space. And that's a perfectly natural consequence of the elements that we now characterize by putting them in a periodic table. So we can look at various elements and we classify them and catalog them according to what's inside those atoms, what the electrons are doing, what the nucleus is made of. Most atoms, certainly most of the atoms you're used to, are stable in the sense that once you've made an atom, that atom exists essentially forever. It might be that you can take a few electrons out or put a few electrons in, but the atom is essentially eternal. Once it's been made, and it might have been made way back in the early Big Bang, and it's been floating around ever since. But there are some atoms that are not stable. There are some that are unstable. They change. Physicists say they decay into something else. By decay, we don't mean they go moldy. They're not the sort of decays that would be prolonged by Tupperware. A decay means it changes into something else. An atom changes into, if you like, a different species of atom. One element changes into a different element. That's what we mean by decay. And in the process of decay, the nucleus of an atom spits out some subatomic particles. Now let's try and visualize that as best we can. We're going to take a few examples. I'm going to pick an example to see radioactive decay. I'm going to pick uranium. So what we're going to do is to switch back to a live demo. So let me switch back to the camera again. So let me go back to this. This is a piece of glass that has been doped with uranium. And if my glamorous assistant would care to hold it up, why do we actually put uranium in glass? Is it because it's radioactive? No, we don't put uranium in glass because it's radioactive. We put uranium in glass because it fluoresces under ultraviolet light. And people think that looks really cool. So they put it into their cabinet and put UV lights in their cabinet, and they get a very attractive piece of glass. It is indeed radioactive. If we just swing the camera around to our Geiger counter and switch the counter back onto audio again. If I put this in front of the detector, let's do it so my hand is not in front of it. It is not particularly radioactive, but there's definitely some uranium in there. So this is a piece of uranium, but unfortunately it's a bit big to go into my cloud chamber. So I just wanted to show you that uranium glass does exist. It is radioactive, but that's not the reason it's bought. What I'm going to do is to pick a smaller piece of uranium, and again, this is not particularly dangerous. It's just a small mineral that's dug out of the ground that happens to contain a small amount of uranium. And I am going to carefully pick it up because it is tiny. Again, if I bring it in front of the Geiger counter, you can see that this is quite definitely radioactive. Okay, so I'm telling you that that's made of uranium. It doesn't really matter what it is. But what I'm going to do now is remember the cloud chamber that we were looking at a moment ago. We were just looking at cosmic rays. Now I'm going to place this sample inside the cloud chamber, trying to do it very carefully, in such a way that we should see the radioactivity. I have just opened up the cloud chamber. The cloud chamber is a system where we're trying to make clouds, hot at the top, cold at the bottom. So there's a heater at the top and a fridge at the bottom, if you like. And I've just opened it up, which has disturbed that nice temperature gradient that used to be in there. So you might have seen that all of this sort of rain, if you like, this cloud formation was disturbed by the fact that I opened up the system. And I'm now waffling and waffling and waffling to give it enough time to stabilize. Hopefully that temperature gradient from hot at the top to cold at the bottom will re-establish itself. So at the moment we can't even see any cosmics in the background, let alone anything else. But if I waffle for long enough, it hopefully will settle down again, and then we will start not only to see the cosmics come back, but we should also see the radiation from this particular sample. So just as before, when you see something come out of that rock sample, give a shout. I'm not sure exactly when it will be. Let's just wait another minute or so and see what happens. Because I can't think of anything else to waffle about just at the moment.
What's the substance that's sat on top of?
The substance inside the cloud chamber is alcohol. So this is just sitting on a black plate, which is cold. So that's the source of cold. There's a heater, which is sitting on the top here, which you can come and have a closer look at in a moment when the talk is done. And the sample is simply sitting on the cold plate, and the rain you can see there, the droplets, are the alcohol that is coming down. We seem to have a little ladybird going in the opposite direction to the cosmic rays. That's just confusing matters a little bit. Yep, okay. Have we got anything coming off our sample yet? It's about time we saw something. When I switched this on earlier, it took a few minutes for for the temperature gradient to set itself up, and having just disturbed it, it could take a minute or two, but I would be hoping that by now we should be starting to see something. I don't particularly want to move on until I've shown you this, because otherwise we'll move on and we'll miss the action, as it were.
What is the specimen you put in there?
This particular specimen, it's a mineral that contains uranium. It happens to be called studite. I had to look it up. So I've got a number of different minerals, which I bought from a mineral shop, as it were, and there's dozens of different minerals that all contain a small amount of uranium. This one is called studite. I'll show you in a moment. Another one called boltwoodite. This one just happens to have enough that it usually produces some nice tracks after a little while. So this particular cloud chamber is one I built myself. It's based on the idea of a cloud chamber, as I'll say in a little while. Cloud chambers have been around for about 100 years or so. And in the early days, they were a very useful way of actually being able to visualize subatomic particles. Up to that point, we had no real way of actually seeing subatomic particles. We had to infer their existence. And it wasn't until cloud chambers came along that we managed to actually see, for instance, radiation coming out of rocks. It was always inferred that some samples, some minerals were radioactive, but it wasn't until cloud chambers came along that we were able to actually see them. And this is taking embarrassingly longer than I thought to actually set itself up. Everything seems to be okay in that the alcohol seems to be evaporating from the top and coming down to the bottom quite nicely. So how come we haven't got our cosmics back yet? Let's just give it another couple of minutes. If any of you are inspired by this talk in terms of being able to see subatomic particles or being able to see cosmic rays that are coming from different parts of the universe, if any of you would like to build one for yourself, I brought along not only a handout of the slides of this talk, I've also brought along instructions for how you can build yourself a cloud chamber like this. This cloud chamber cost, when I bought the components off Amazon, a heater for the top, a fridge for the bottom, etc., piece of glass, it costs about 30 to 40 pounds, depending on what bits and pieces you already have lying around. Still nothing? Oh, did you see that one? Yeah, okay. So it's taken a little bit longer than usual, so my waffling can now come to an end. So now we can see the radioactivity of this particular particle. So we had a couple of flashes to the bottom left. And as time, whoop, do you see that one? So now you notice that they're coming out thick and fast. Once the conditions have stabilized, and it took perhaps 5 minutes for that to actually happen, we're now seeing all of the radioactivity of this particular sample. It doesn't take too much imagination to realize it's coming from the sample, because all the tracks seem to end where the sample is. If you occasionally see a track which is unrelated to the sample, that's just another cosmic that we saw before. But in this particular case, you can see an awful lot coming out of this sample. Perhaps you noticed there were two different varieties of things coming out, yeah? Sometimes very sharp, very narrow, very bright. Sometimes a little bit more broad, a little bit more ghostly, yes? So not only can we tell that this particle is spitting out, this mineral is spitting out something, some particles, it seems to be spitting out two different types of particles because they seem to be making different tracks. And regardless of what the cause is, they seem to be falling into two families. So that's one of the things that was determined by building cloud chambers, is that you can tell something about the nature of the particles that are being spat out by a radioactive material. You can see now that things have stabilized, that an awful lot is coming out of this particular particle, this particular mineral. So let's go back and ask ourselves what is actually going on. So this is a video I made earlier, just in case the cloud chamber didn't work. Not that I haven't got any confidence in it, but in good Blue Peter fashion, earlier I put a different rock. This is a boltwoodite sample, but again, it's made with some uranium. And again, you can see various particles coming out. There was something in the bottom right that was unrelated to the mineral, so presumably that was just yet another cosmic. When I took this video, I let it run for quite a while, quite a few minutes. and then I went through it and simply composited all of the tracks that I could see over a course of a couple of minutes and put them all together so that you can get a better idea of what was going on. Again, you can see two different families of particles. You can see very narrow tracks coming out, and you see these more ghostly ones in the background. So again, not surprisingly, it's not the same mineral, but it's got the same atoms in it, and therefore you're getting something coming out. But the question is what? It's clearly emitting something, and it apparently is two families of something, but what are the particles and where do they come from? So we have to remind ourselves of what atoms are, and that's not a particularly accurate indication of an atom, but it's good enough for our purposes. If an atom is simply a nucleus, and a nucleus comprises protons and neutrons, and the nucleus is surrounded by a whole load of buzzing electrons in a cloud, when it comes to radiation and radioactivity, for instance, uranium and other radioactive particles like that, other radioactive atoms, it is only the nucleus that determines the radioactivity. It's nothing to do with the cloud of electrons around the outside. So we have to look at basically nuclear physics to understand radiation. Now, okay, there's an awful lot going on in here, but the bottom line is some nuclei are unhappy being what they are. If a nucleus is a whole bag full of protons and neutrons, some atoms are happy with that, and they just want to keep the protons and neutrons they've got. But some atoms are unhappy. They are unstable because they want to change into something else. And in order to change into something else, a nucleus can do lots of different things. For instance, it could spit out a proton. It's got a certain number of protons and a certain number of neutrons. This is quite a heavy nucleus here, nucleus of a very heavy element. It might spit out a proton. Alternatively, it might spit out a neutron. We're not going to go into the nuclear physics of why it decides to do one rather than the other. It might decide that it's so unhappy being what it is, it wants to spit out more than one proton or one neutron. It might spit out 4 at a time, 2 protons and 2 neutrons. That particular particle is called an alpha particle. So an alpha is simply the name we give for that particular combination of fundamental particles, of components of a nucleus. I shouldn't call them fundamental particles. 2 protons and 2 neutrons is what we call an alpha. And it's also possible that a nucleus might spit out an electron. Bear in mind, electrons do not exist inside the nucleus. What we mean by spitting out an electron is a proton might change into a neutron, or a neutron might change into a proton, and in the process, an electron is born. So these aren't anything to do with the electrons that are buzzing around outside the nucleus. These are still nuclear particles. They just don't exist inside until a proton decides to become a neutron or vice versa. These so-called beta particles, they're called beta originally, but we now know that they're electrons. So we could either call them electrons or we could call them beta particles. Betas come in 2 flavors. Either they're the negatively charged variety, which is our familiar electron, but there's also a positively charged variety, which is the antimatter equivalent of an electron. And nucleus of a material, nucleus of a particular atom, might spit out the antimatter equivalent of an electron. It is also possible that a nucleus that is unhappy being the way it is might spit out something else, a gamma ray. A gamma ray is rather different because a gamma ray is just an electromagnetic wave, unlike these other objects which are basically particles. Now, according to quantum mechanics, you can argue whether waves and particles are the same thing, but most of us would consider an electromagnetic wave as being quite distinct from these other particles which can be spat out by a nucleus. So we're not going to consider all of those possibilities. I'm just saying that in that previous slide that there are lots of things that a nucleus can do. Let's just very briefly just think about the most popular, the most likely ways that you can get radiation out of a material, so-called alpha, beta, or gamma. We've already said that alpha is basically just 2 protons and 2 neutrons that are, if you like, stuck together in a particular structure. We can either simply label it as an alpha particle, or we could call it, this is the same as the nucleus of a helium atom, because the nucleus of a helium atom is 2 protons and 2 neutrons. One thing to bear in mind throughout this talk is that it doesn't really matter if we call them alpha rays or alpha particles. In the early days of cosmic radiation, it was assumed that all of these things were rays, in much the same way you talk about cathode ray tubes for the electrons at the back of a TV, for instance. But it really doesn't matter whether words that you use are alpha particles or the words you use are alpha rays. They are effectively interchangeable. But alphas, because they're made of 2 protons and 2 neutrons, are quite heavy, so they don't travel far through materials. In fact, they can barely pass through a few centimeters of air. Betas, beta rays, beta particles if you prefer, or you can just call them electrons. Then they are very lightweight particles. Electrons are much less massive than protons and neutrons, and they can penetrate further than alphas. They still don't travel that far through air, but they can travel farther than than alphas. And gammas are these electromagnetic waves, so they're different in character from the alphas and the betas. So now that we know what it is we are talking about, if we switch back to the actual sample, we now know that the alphas, which don't travel very far, are basically bulldozers. They are very massive, 2 protons and 2 neutrons. They are responsible for the rather broad, somewhat more ghostly tracks. The electrons are traveling quite energetically and produce relatively straight, relatively narrow traces in the cloud chamber. So we can distinguish between alpha and beta radiation. It might be that this particular sample is also producing gamma radiation, but gamma is not a charged particle. Remember, alpha has charge, beta has charge. As it happens, one is positive, one is negative, but gamma is an electromagnetic wave. It doesn't have any charge, so when it comes through a cloud chamber, it doesn't leave a trail behind it because it's not a charged particle. So we're only seeing alphas and betas, even if this particular sample is generating gammas as well. Now, because I want to see cosmics later, I'm going to take this sample out, and that will give the chamber a little while to settle back down again. So let me take the sample back out. And I'll put all of these samples away safely out of your way so that you can come down a little later and have a look. Okay, so now we've had a look at alpha and beta. Let's go back. And again, just in case it didn't work, here's the reminder, and let's go on from the video to the still. So the ghostly tracks in the background, these are alphas, and they look pretty much the same if you saw them as a cosmic ray, and not as a cosmic ray, if you see them without a radioactive sample in place, and these are the betas, which you do see in cosmic rays. Notice that some of them look rather curved. That's just an illusion because we're in a cloud chamber and the cloud is forming and dropping. All the droplets are dropping under gravity, and so as these tracks form, they tend to often look curved, even if the electron is basically traveling in something akin to a straight line. So we can tell the difference by looking at the tracks of these things. So let's just finish with a thought about radioisotopes. One thing I forgot to actually bring out, let me see if I've still got it to hand. I can't remember now which pocket I put it in. Let me just have a quick look. There's one of my radioactive samples. So isotopes are simply cousins of the same type of atom. So for instance, if we take a specific example so you can see what I'm talking about, if we think, for instance, of carbon, then with carbon we have 6 protons in the nucleus because by definition any collection of 6 protons is what we call carbon. Carbon is simply the name we give to any entity which has got 6 protons in it. If a carbon atom has a nucleus with 6 neutrons, then that's a stable isotope which we call carbon-12. It's called carbon-12 because if we have 6 protons coloured red and 6 neutrons coloured blue, we have 12 in total, and that isotope is called carbon-12. If we have another type of carbon, still with 6 protons, but now if we had, hypothetically, what if we had 8 neutrons? This would be called carbon-14. 6 protons and 8 neutrons gives us 14. This particular isotope of carbon is radioactive. It's unstable. This is the one that's used in carbon dating. If we want to know how old a tree is, or not a fossil necessarily, but something old and made of something organic, we can use the radioactive decay of carbon-14 to work out how old it is. So carbon-12 is mainly what you're made of. you have a little bit of carbon-14 in you, and that's how we date organic materials. So having different isotopes of atoms is quite useful. Now, in terms of isotopes of some radioactive elements, there are three that dominate how much radiation comes from the Earth. The first is potassium. That's one of the most abundant of the radioactive elements. In your body, of course, there's a fair bit of potassium. There are some foods which are very rich in potassium, such as bananas and Brazil nuts and a few other things. And for instance, in the average person, if you work out, because potassium is radioactive, certain isotopes of potassium are radioactive, it can be worked out that there are probably 4,000 atoms in your body decaying every second, changing into something else, potassium changing into argon. 4,000 sounds a lot, perhaps, for every second, but remember just how many atoms there are in your body. It's a tiny amount compared to the total. And potassium decay, potassium radiation, is one of the largest contributions to background radiation. The other two elements are thorium and uranium. Thorium is more abundant than uranium, and uranium is probably more abundant than you think. You tend to think of these things as being very rare. Surely there can't be much uranium in the ground. Well, actually, uranium is very abundant in the sense that there's 500 times as much uranium as there is gold. 3 parts per million doesn't sound very much, but gold is way less than that. Gold is 500 times less than 3 parts per million. So we're prepared to dig gold out of the ground. It's rather expensive to dig uranium out of the ground. There's the obvious benefits in terms of using it as a nuclear fuel, but there is actually more of it. It's just rather tricky to get out. Gold occurs naturally as a metal. Uranium has to be processed. At the Earth's core, we have potassium and thorium and uranium all contributing to the heat in the Earth's core. Each of these elements is decaying, producing heat. It generates energy, it generates energetic particles, which keeps the core warm. It keeps the core molten. So the radioactive decay of these elements is keeping the Earth's core molten. It's got nothing to do with heat from the sun. The reason we have a molten core 4.5 billion years after we've been made is nothing to do with the arrival of energy from the sun. It is entirely internal. So if you have a molten core, a rotating molten core basically is a dynamo that generates the Earth's magnetic field. So we can thank the Earth's magnetic field to the radioactive decay of elements in the core of the Earth. It's rather perhaps ironic or rather poetic that the Earth's magnetic field partially protects us from cosmic radiation. So we are partly protected by radiation outside the Earth by the Earth's protective magnetic field. But the Earth's protective magnetic field comes from radiation in the Earth's core. So radiation provides us with protection from radiation. It's an interesting sort of cycle of life. Just as an aside, as it were, there is one particular isotope of potassium. There's only a small amount of it, 0.01%, but 0.01% of potassium is a particular isotope called potassium-40. And it's an isotope that emits beta plus radiation. Beta radiation, remember, is electrons or their antimatter equivalent. If the particle is negative, it's an electron. If the particle is positively charged, it's an antimatter equivalent of the electron, an anti-electron, if you like. The same as an electron in all respects, except it has the opposite electrical charge. So basically, it's antimatter. So anything that contains potassium is generating antimatter. Not much. If I put it in front of the Geiger counter, you wouldn't be able to measure how much. But the bottom line is any food rich in potassium, such as bananas or Brazil nuts and quite a few other foodstuffs, they will all be generating antimatter. And that's one reason why we now have a banana equivalent dose, which some people invented just to give an idea of how much is this radiation. Well, let's equate it to how much radiation is produced by a banana. In other words, how much radiation do you receive by eating a banana? Take that as one unit, and then you can relate other units to that. I'm not going to take too many as that, but let's just take one example. If eating a banana is that much, then what are you receiving as a result of cosmic rays? Everybody on Earth receives, roughly speaking, the same cosmic ray dose. And the total amount of radiation you receive in one day compared to a banana is roughly 2 hands of a banana. In other words, the cosmic ray dose you receive is some 10 times higher than the dose you would receive if you simply ate a banana and absorbed the radiation from it. Bear in mind that's not entirely true that it's universal, because you'd have to say, well, actually it's rather higher. The cosmic ray dose would be rather higher if you spent a lot of time in an aircraft. At altitude you receive a larger cosmic ray dose, which is why pilots have to be careful as to how many hours they put in at altitude, because they will be receiving more radiation than the rest of us. And the final point before we move back from terrestrial back to cosmic rays proper is that not all sources of radiation are from solid materials such as potassium or thorium or uranium or foodstuffs. There is one other source, and that is a gas. Radon is a radioactive gas which is effectively pretty much everywhere. It comes from the radioactive decay of a small amount of uranium. And uranium, again, is everywhere, not in large quantities. In England, there's not an awful lot of uranium in the ground, but it is pretty much all over the world in all rocks. Radon concentrations do vary across England. The red is the highest radiation dose, and the sort of blue colour is the lowest radiation dose. And you can see in Cheshire, it's pretty low on the whole. Same in Wirral, same in most of the West Midlands. And if you notice where the red patches are, they tend to be mountainous areas, either the Pennines or Cambria or the southwest, Cornwall and Devon, etc. If you have a lot of granite, granite contains uranium. Uranium produces radon, hence radon is in the atmosphere and is especially high concentrations in these sorts of areas. But even in this background area, we will still see radon occasionally in the cloud chamber. We can tell it's radon because, remember, alphas don't travel very well through materials. They only travel a few centimeters in air. Alphas will not get through the glass of the cloud chamber, so they can't be generated outside. They can't be generated by cosmic rays and then enter the cloud chamber because they wouldn't get through the glass. So anything we see in a cloud chamber has been generated inside because of radon gas, which is inside the cloud chamber, because radon gas is inside this room. Just to, roughly speaking, how many radon atoms are there in this room? Probably less than 1 billion, which might sound like a lot, but compared to the number of atoms in this room, it is an absolutely tiny fraction. So we know that radon levels are high where you have a lot of granite, and radon emits alphas, and hence we can identify the presence of radon in a cloud chamber simply by knowing that it can't be cosmic derived, because cosmics won't get through the glass of the cloud chamber. So we're done thinking about terrestrial sources of radiation, so let's move on to proper cosmic rays. So the pioneers of radiation were these people. I think everybody will know Marie Curie. Some of you might know Henri Becquerel. Perhaps very few people have heard of Victor Hess. So Becquerel discovered radioactivity by noticing that any photographic plates that came close to radioactive materials, like pitchblende, for instance, started to fog, even though they were entirely encased and not ever exposed to light. Marie Curie synthesized various radioactive elements, including radium and polonium. And the role of Victor Hess was perhaps less well known. But back in the late 1800s, a lot of people were playing around with radiation, and it was noticed that electroscopes lost their charge. What's an electroscope? Well, a gold leaf electroscope is basically a couple of thin sheets of gold leaf inside a sort of bell jar to try and stop air currents making a difference. If you charge them up, if you put the same charge on both of the gold leaves, like charges repel, and so the two gold leaves will separate. It was noticed that if they did that by applying some charge and seeing the gold leaves separate, it was noticed that they would slowly collapse, indicating that extra charge was being added or removed from the little bell jar there. So they were trying to work out, if I charge this up, why does it leak away? Where's this extra charge coming from that will neutralize my electroscope? Is this extra charge, is this extra radiation of charged particles, whatever they may be, is it coming from above or is it coming from below? Well, a physicist called Theodore Wolff back in 1910 said, right, we're going to figure this out. What we're going to do is have an electroscope at the bottom of the Eiffel Tower and see how quickly these gold leaf electroscopes discharge. Then we'll do the same experiment at the top of the Eiffel Tower. If everything is coming from the ground, we would expect that the top of the tower is so far away from the ground, it shouldn't produce any radiation, and therefore we would see our electroscope not discharge. But things didn't quite work out quite so clearly. There was a change, but the radiation levels decreased by far less than you would expect if the radiation was coming only from the ground. And then the big question was, well, why is it so complicated? Is it because the tower itself is radioactive? Is it because the atmosphere is radioactive? Well, at this point, radon was already discovered, so people knew that the atmosphere was radioactive, but they didn't think that was the consequence, that was the cause of these electroscopes discharging. And it's not so silly to say, is the Eiffel Tower radioactive? The Eiffel Tower is made of iron. Iron is dug out of the ground. We know some things in the ground are radioactive, so it's not unreasonable to say, is it possible that the Eiffel Tower is radioactive? So the bottom line is that experiment was inconclusive. And this is where Hess steps in, and he figures out if we're going to determine where this radiation is coming from, the Eiffel Tower is not high enough. That's not enough to discriminate whether things are coming from above or coming from below. So if we want to resolve that question, we need to go higher. So he designed detectors that were capable of working at high altitude, and in 1911 and 1912, he put these detectors on balloons and went to various heights to see at what point his electroscope would discharge, indicating more radiation. In 1911, he went up to about 1,000 meters and didn't really see that much change. So perhaps no surprise that the Eiffel Tower experiment was a bit inconclusive, because even if you go 1,000 meters, it's not obvious whether the radiation levels are going up or going down. But when he went to 5,000 meters, it was absolutely obvious that the radiation levels were starting to increase quite dramatically. So at this point, it was quite clear that the principal radiation that you measure to discharge an electroscope was coming from above. That doesn't answer the question of where it's coming from. It just basically says the effect of the ground is minuscule. Yes, the ground is radioactive, but in terms of background radiation, most of it seems to be coming from the sky, not from the ground. But if it's coming from the sky, can you tell if it's coming from the sun or coming from something other than the sun? It was thought that maybe the sun would be a source of particles. How are you going to tell? Well, if you've gone to 5,000 meters and you know the radiation levels increase, if you want to know whether it's the sun or not, what do? Some people might say, well, fly at night and then see what happens. Anybody who intends to take a hot air balloon up in the middle of the night, where you can't see where you're going and you can't see where you're landing, will realize that's not a good idea. So Hess had a brilliant idea. You don't go at night, you go on a day when there's a solar eclipse. Brilliant. You measure the radiation levels, you wait until the moon covers the sun, and you see if the radiation levels go down or not. Nobody could believe that any radiation from the sun could possibly get through the moon, so if the moon covers the sun, the radiation level should fall if the radiation is coming from the sun. The radiation levels didn't fall during the eclipse. He deduced that the radiation is coming from somewhere beyond the sun, or at least most of it is coming from beyond the sun, even if the sun is producing something. So in 1936, Hess got the Nobel Prize for basically discovering cosmic rays or cosmic radiation. They weren't originally called cosmic rays, but by the 1920s, everybody was calling this radiation from above cosmic rays and cosmic radiation. Even though they didn't know what it was, they knew it was cosmic. So now we have a better idea of what's actually going on. We know that although this artist's impression is a rather poor artist's impression for a number of reasons, it gives us an idea of what's going on. Some distant source is producing radiation, and when that radiation hits the top of the atmosphere, it produces a cascade of secondary particles. In other words, this is an artist's impression. Ignore the fact that there seem to be two showers at the same time. That doesn't seem very likely. Let's just concentrate on the one on the right. A single particle coming in will hit one of the atoms in our atmosphere, which will produce a few more particles, which produce more particles, which produce more particles. There's a cascade, an avalanche effect, if you like, of particles being generated, and this is called an air shower. This is a very simplified diagram on the right, because as we've seen from the artist's impression previously, there could be lots of these secondary particles. But what happens is something is coming in and hitting our atmosphere. We call that a primary cosmic ray. And it collides with atoms in the upper atmosphere and produces a cascade of so-called secondary particles. And each level of this cascade, very much simplified on the right, we might get one particle producing 4, and then each of these produce 2 or 4, and each of those produce 2, and you can see how it multiplies into an avalanche effect. So you end up with a huge number of particles reaching ground level. Each level of the air shower, the new particles share the energy of the incoming particle. Hence, if we measure what's going on at ground level, we can reconstruct what must the energy of that initial particle have been to give us all the particles we see arriving at ground level. One incoming particle won't produce half a dozen secondary particles, it will produce thousands or possibly millions of secondary particles arriving down at ground level. What are these secondary particles? Well, it might be a few of the particles that we're already familiar with, the constituents of atoms. It could be that these secondary particles are protons or electrons, but some of them are particles that do not exist in atoms. For instance, some of them are unstable. Some of these secondary particles that are being generated are unstable and might only live for a tiny fraction of a second. The most common of these are called muons. They're not part of atoms. They are made in cosmic rays and can be made in other ways, but they're not part of you and me. They are made in cosmic rays. They only last for a fraction of a second. A muon is like a sort of distant cousin of the electron. It's similar to an electron in many of its characteristics, except it's much heavier. It's 200 times the mass. And a muon will not live for much more than a couple of microseconds or so. So it's very much a fleeting existence, but it's long enough for the particles to make it to ground level, and it's long enough to make a click in a Geiger counter or to see them in a cloud chamber. That's what we might see. This is an individual picture from a video I took a long time ago, and that's what we might see for a muon, a whole load of droplets that indicates the track of where the muon moved through the cloud chamber. They tend to be straight, unlike electrons, which tend to be much more like sort of a pinball machine, much more wiggly, much more erratic. So anything that looks like a very straight line is probably a muon going through the cloud chamber. So that's what we see at ground level, but what about the primaries? So far we've been thinking about what we see in a cloud chamber and clicks in a Geiger counter. All of this is at ground level, so that's not what's actually coming in at the top of the atmosphere. Well, the primary particles themselves, the ones that create the showers, over the last few decades, we've done a lot of research and placed instruments above the atmosphere to see what is raining down on us. And now we've determined that most cosmic rays hitting the atmosphere are protons. In other words, most of the incoming cosmic rays are the nuclei of hydrogen atoms. About 9% of them are alpha particles, or if you prefer, they are the nuclei of helium atoms. And the remainder, after we've taken away 90 and 9, the remaining 1% of all cosmic rays are the nuclei of heavier atoms. What type of atoms? Well, essentially all of the ones we see around us. Lithium, beryllium, boron, carbon, nitrogen, oxygen, etc., all the way up through the periodic table. Okay, not many of them, because all of these heavy nuclei only contribute about 1% of all cosmic rays, but as far as we can tell, what's raining down on the top of the atmosphere are the nuclei of the sort of atoms we see around us. So from wherever they're coming, out there, the universe is made of the same sort of stuff as what we see in the solar system around us. So let's think about detecting cosmic rays. We had a look at this earlier, this so-called Geiger-Müller tube or Geiger counter. What's actually going on in there to make the clicks? Well, we have some incoming radiation, and if that radiation is a charged particle, it will ionize some of the gas inside. The gas is usually an inert gas like argon or something like that. We can ionize the gas atoms inside, and by putting a voltage between the inside, the middle of this tube, and the outside, then if we do generate an ionized atom, the plus will go one way, the minus will go another way, and we'll get a current flowing. And that current is simply converted by the yellow box into a click for our convenience, as well as telling on the meter how many particles we've received. It'll give us a click every time it sees one. So that's all a Geiger-Müller tube really is just gas that responds by getting ionized by the incoming radiation. What about this cloud chamber? Well, this was Charles Wilson. Allegedly, back in 1894, it is said that he went onto the top of Ben Nevis and saw the Brocken spectre. When you look at your shadow from the top of a mountain, if it's a very moist environment, if you're in the middle of a cloud, for instance, you might see your shadow and then you see this halo around it. He was very interested in these phenomena, and he thought, rather than do all his research on the top of Ben Nevis, why doesn't he make a cloud in the laboratory rather than have to go up a mountain? So he figured he would develop the idea of a cloud in a jar, a cloud in a chamber, so that he could basically start studying optical phenomena such as these halos. And in 1911, he developed the first cloud chamber. That's pretty much what it looked like. I'm not going to go through the mechanism, but basically he had water vapor in a chamber and used it to study optical effects. Now, the key thing is that after he built his cloud chamber, one of the first things he noticed was that every so often he got a contrail going through his cloud chamber. When a charged particle passed through, water droplets condensed to form visible tracks. This is pretty much what happens when you've got water vapor in the atmosphere. An aircraft flies by at high altitude, it leaves a contrail. It leaves a condensation trail of droplets. That is pretty much what's going on here, a condensation trail of droplets. In Wilson's case, it was water. I find it more convenient to use alcohol when we're trying to reproduce his experiments here. But the key observation was charged particles passing through leave tracks, so you can watch them, you can see what's going on, you can deduce interactions between particles if you can see where they've come from and where they're going. As a result, cloud chambers had a huge impact in experimental particle physics, because experimental particle physicists assumed these particles exist. Now they could actually watch them and see how they interact with each other. And so in 1927, Wilson was awarded the Nobel Prize in Physics for, what a quote, the most original and wonderful instrument in scientific history. That's quite a citation, isn't it? It's just changed a little bit. So that's the original 1911 model on the left-hand side. This is my version of it, the 2024 model, sitting on the table here, producing the tracks that show us cosmic rays and the radiation from alpha and beta radiation from a mineral. So my cloud chamber is a rather distant cousin from Wilson's original. I'm not going to go through the details of how I designed and constructed it. That might one day be a short talk all of its own right. But that's basically a section through it. That's what it looks like on the front bench. Basically, it's a heater on the top and a little fridge unit run with Peltier modules to keep the bottom cold. So if you can keep the top at plus 35 and the bottom at minus 25, and put some alcohol on the sponge at the top, the alcohol evaporates, will condense as it falls towards the cold plate. Little cloud will form and drizzle will slowly fall down onto the cold plate. If you're lucky, just before it hits the cold plate, the conditions will be just right so that droplets are wanting to form, and the passage of a charged particle will just trigger that in much the same way that an aircraft flying at altitude will trigger the formation of a contrail. So let's just remind ourselves, if it's decided to sort itself out, we should be back to square one, and we will occasionally see cosmic rays coming through. Now that I've removed the radioactive sample, that's far enough away. Let me just guarantee it's far enough away by moving it. The radioactive samples are now nowhere near the cloud chamber, and so what we're left with, these little tracks that we occasionally see, sometimes a short track, sometimes a long track, we're now back to seeing the original cosmic rays. We are fairly sure that the cosmic rays are either electrons or protons or muons. We might occasionally see an alpha particle, but remember the alpha particles are coming from radon, not from the cosmos. So we can switch back to this a little later if we want to see what more cosmic rays we can see. But let's continue as it stands now with the talk. So this is again a video I made a little while ago just to see what sort of things we see. Occasionally we said that was an electron because it wasn't straight. That was a nice proton going through the right-hand edge. Again, this is just a video showing roughly what you can expect to see. Just like with the rock in the middle of the cloud chamber, what I have done some months ago is take quite a long video, not just a few minutes, but basically an hour's worth of video, and said, how many tracks do I see in an hour? And the answer is lots. So again, these are hundreds of tracks. The really bright ones are protons. The straight ones, which are almost lost in the spaghetti in the middle, are muons, and all of these rather more wiggly tracks are electrons. Every once in a while, you can't tell perhaps, but every once in a while you see a V, indicating that two particles have come out of, not nothing, but have come from a particle that you can't actually see. Is it possible that a gamma ray has produced an electron and an anti-electron? Possibly. It's difficult to be definitive. But you can definitely see an awful lot of physics going on if you watch a cloud chamber for many minutes or half an hour or so. Cosmic ray experiments are being done all the time, not just by amateurs with cloud chambers, but for instance, Voyager 1 and Voyager 2 had cosmic ray experiments on them up there in the red, the very top of the diagram there. Cosmic ray experiments were flown on Voyager, partly to see what sort of flux we get from planets, but as much as anything, what is it like in between planets? As they flew through the solar system, they were continually recording the cosmic ray flux to get an idea of how it changed as you move away from the sun and go further and further into the outer solar system. Back in 2012, Voyager 1 measured a sudden change. It noticed a sudden decrease in the low energy cosmic rays and a sudden increase in the high energy cosmic rays. And that was taken to be an indication that it had left the influence of the solar system and was now effectively flying in interstellar space. The same was true for Voyager 2, but that is traveling rather more slowly. Voyager 2 is traveling about 10% slower than Voyager 1, so it took a little longer to reach the point where it left the solar system. So it wasn't until 2018 that Voyager 2 was declared to have left the solar system based on cosmic rays. What was actually seen was the low energy cosmic rays suddenly took a nosedive, and the high energy cosmic rays started to grow and then again made a little bit of a jump just when the low energy cosmic rays seemed to dive. So we seem to be indicating that the low energy stuff comes from the sun and the high energy stuff comes from somewhere else. So that was taken as the point in November 2018 at which Voyager 2 left the solar system. There are experiments up on the space station. That's it on the bottom right there, AMS. AMS stands for Alpha Magnetic Spectrometer. You can get an idea of how big this cosmic ray detector is because of the astronaut sitting on the top left there. Basically, it's looking for cosmic rays coming through this particular cylindrical tracking device, and that tells us what and how often particles are arriving before they hit the atmosphere. So we can do experiments on the ground, but by having experiments on the ISS, we can tell what is actually arriving from the top of the atmosphere. Ground-based cosmic ray observatories, there are quite a few around the world. One is called the Pierre Auger Observatory, and it's in Argentina. And again, this is just an artist's impression on the right-hand side, indicating that if a particle comes in, it produces an air shower, which can then be picked up by these ground-based detectors. Now, if you want to make sure you pick up most of the contents of an air shower, you need to make sure your detectors, these are actually detectors full of water, I'll come back to that in just a second. What sort of area do you need? Well, you need a very large footprint to make sure you catch a reasonable fraction of the air shower. It's no good just having something over a few hundred square meters because you wouldn't be picking up all of the air shower, and it would be very difficult to work out what's coming in at the top of the atmosphere if you're only reading a tiny fraction of the air shower at ground level. So what they decided was we need a very large footprint, so they spread these detectors over a very large area. What does a very large area mean? Well, in Argentina, real estate isn't too difficult to come by, so they decided to spread these detectors over the area equivalent to the area of Luxembourg. That gives you an idea of just how big this observatory is. How do they detect the passage of a cosmic ray through these water detectors? It's the same idea as how do you actually see a particle like an aircraft traveling through the air faster than sound can travel through the air. If an object moves through the air faster than the sound can travel through the air, you get a shock wave. And the same is true if a cosmic ray particle travels through water faster than light can travel through water. You get the photonic equivalent of a sonic boom. You get a flash of light. So regardless of whether you're traveling through water or through air, you can see this type of radiation. It's called Cherenkov radiation. If we imagine what happens when a hypothetical cosmic ray particle comes in and hits the top of the atmosphere, this is what happens next. The particles can travel faster than light can travel in the air, and you get a photonic boom. It's a blue flash of light. Cherenkov radiation or Cherenkov light. But it is just a flash, a billionth of a second or so. So if you want to see it, you need big telescopes. There's a whole set in the Atacama Desert. There's a whole set being built in the Canary Islands called the Cherenkov Telescope Array, looking into the air to see cosmic ray particles traveling through the air faster than light can travel through the air. And what they look like is something like that. Not all of them are built yet. They're still under construction. Some small and large telescopes in La Palma and another mixture of telescopes in the Atacama Desert. So essentially the whole sky is covered. And hopefully they'll be able to see this blue flash, this Cherenkov radiation, and be able to deduce, by looking at that, what particles are arriving at the top of the atmosphere. So you can do it through water, as indicated in the Pierre Auger Observatory. You can do it in air. You can also do it in water that isn't liquid. You can do it in ice if you so wish. So at the South Pole, there is an experiment called Ice Cube. There's a laboratory on the top of the ice cap. There's the rock of Antarctica, and it looks like our ladybird is back. So there's the rock of Antarctica, there's the top of the ice sheet. What they've done is instrument by putting a load of photodetectors drilled down into the ice and strung like loads of strings of pearls. So effectively they have a large cube of ice, 1 kilometer by 1 kilometer by 1 kilometer. That's why it's called Ice Cube. It's effectively a very large ice cube. And they've instrumented it so they can see any cosmic rays coming through that cube where the cosmic rays would be traveling faster than light can travel through the ice. And just for scale, there's the Empire State Building, just to give you an idea of how large this ice cube is. So the idea is if you get a particle coming through, it'll produce Cherenkov light, and that Cherenkov light will be picked up by the photodetectors. So you look at which particular photodetectors pick up the light, and from that you reconstruct where this particular particle came from, and you reconstruct how much energy would it have to have had in order to set off the photodetectors in the following way. So that leads us to, well, where are these coming from? Now that we know that we can detect them, how do we know where they're coming from in the first place? Just as a very quick aside, remember that it's something like 100 years ago that Hubble gave us a clue as to the size of the universe. It's only a few months away, the 100th anniversary of Hubble saying, if you look at variable stars in Andromeda Galaxy, we can show that these so-called spiral nebulae are not part of the Milky Way, they are galaxies in their own right. That was the nail in the coffin of the great debate from the 1920s. So what's that got to do with cosmic rays? Well, remember Hess showed that most of cosmic rays are not coming from the sun, they're coming from somewhere more distant. So the question is, well, where are they coming from if they're not coming from the sun? So originally it was where in the Milky Way could they be coming from? But now that Hubble has told us, well, it's not just the Milky Way, the universe is far bigger than the Milky Way. The Milky Way is just one galaxy, and all these other spiral nebula that we can see are galaxies in their own right. So there are billions, if not trillions, of other galaxies out there. So effectively, we can reformulate the question and say, cosmic rays, are they coming from galactic sources, i.e. within the Milky Way, or are they coming from extragalactic sources, i.e. other galaxies beyond the Milky Way? Well, we know there are very violent things out there, such as supernova, which produce shock waves as they go off, and we know that there are jets coming from supermassive black holes at the center of galaxies. So we know that there are lots of ways in which you can generate shock waves. And one thought is that maybe these shock waves, either around a supernova or possibly close to a supermassive black hole, maybe these shock waves are responsible for accelerating particles up to very high energies. I'm not going to talk through the diagram on the right. It's one hypothesis for how particles might be accelerated by a shock wave moving through a plasma of particles, but we're by no means certain that that is the explanation. That's one possible explanation. But when it comes to supermassive black holes, we have to remind ourselves just how violent they are. If we look at this galaxy, Hercules A, that was imaged by the Hubble Space Telescope some years ago, we believe there's a supermassive black hole right at the core of this particular galaxy. The galaxy is rather larger than the Milky Way. This galaxy here, if it was at the same distance, that would be perhaps the size of the Milky Way, the one just below center. So you can see that Hercules A as a galaxy is rather bigger than the Milky Way. But if there is a supermassive black hole at the center, that would be tiny, remember. It would only be about the size of the solar system. On this scale, it would be absolutely minute. And yet, there's enough energy pouring out of that supermassive black hole to produce jets which are visible on that scale, millions of light years. Even though the supermassive black hole is tiny on this scale, the jets it produced have gone across the galaxy and come out of the galaxy and have slammed into the intergalactic medium to produce these shock waves here. So you can imagine just how much energy must be pouring out of that supermassive black hole right at the center of the galaxy. So we don't understand the mechanism, but perhaps that is the engine that is driving the most energetic cosmic rays. So surely working out where they're coming from should be easy, yeah? All we have to do is to measure a few cosmic ray showers, work out where they're coming from, and extrapolate it back, and that's the source that we should be looking at. So simple. Well, unfortunately not, because unfortunately the universe is full of magnetic fields, and magnetic fields deflect charged particles. The magnetic fields are pretty much everywhere. We know there's a magnetic field around the Earth, and we know that tends to deflect some particles. That's why we get aurora, because charged particles are guided by the Earth's magnetic field. So we know we can see, for instance, the magnetic field around a bar magnet by using iron filings. As it happens, we can do something very similar with the Milky Way. The Planck telescope can actually see polarization of light, and that gives us a sort of idea of where the magnetic field lines in the Milky Way are. And it is pretty chaotic. It's nowhere near as simple as the magnetic field around the Earth, for instance. It is thought that the magnetic fields in a galaxy are extremely complicated. And if particles are bent by magnetic fields and the magnetic fields themselves are complicated, perhaps we've got no hope of working out where these cosmic rays are actually coming from. If we look at other galaxies, it's the same sort of picture. Sophia has imaged what appears to be the magnetic field lines of another galaxy, and again, it's rather chaotic and difficult to work out what exactly is going on. When we start talking about what's going on between galaxies, it's even more complicated. We don't necessarily have a whole load of dust that allows us to track what does the magnetic field between galaxies actually look like. So this is, again, just an artist's impression. We've got no real idea of what those magnetic fields are. But we could say, maybe we can get around this problem, because we would assume the most energetic cosmic rays, it's a physical principle that if a charged particle is bent by a magnetic field, the more energetic the particle, the less it's deflected by the magnetic field. So maybe we have to give up on the idea of ever seeing the low energy cosmic rays where they're coming from, because their paths are scrambled, but maybe we have a chance with the highest energy stuff. The catch being, how many are we expecting to see as a function of energy takes a nosedive quite rapidly. We believe the low energy stuff, we're just going to get rid of that unit because it's a silly unit. We believe the low energy stuff might be solar, the middle energy stuff might be galactic, and the really high energy stuff might be coming from outside our galaxy. What is this scale down here? Physicists are very happy with the scale of EV, but not everybody likes that scale. So let's just remind ourselves that the light that's currently hitting my hand from the projector is visible light, and that has an energy of about 1 eV. We don't have to worry about what eV stands for. It's just a unit of energy. If we had light that was 1,000 times as energetic, we would be talking about X-rays. If we have particles whose energies are 1,000,000 times the energy of a visible photon, we'd be looking at the energies of an alpha or a beta or a gamma particle, for instance. But cosmic rays have an enormous energy, anything from 1,000,000,000 times as much to 10 to the 12, 10 to the 15, 10 to the 18, a huge range of energies, including some unbelievably high energies. And just for context, the Large Hadron Collider has an energy around here, and the next particle accelerator that people would like to fund if they can get the money is the Future Circular Collider, and that's where the second arrow is. So these high energy cosmic rays are way higher than the sort of energies that we can generate for particles here on Earth. But the catch is the most energetic ones, which are the ones we'd really like to use, are very unlikely because this low flux. Roughly speaking, this low energy end, we might get 1 particle per square meter of the Earth's surface per second. That's hitting the top of the atmosphere. At the higher energy, we might get 1 per square meter per year. And if we go to the very high energies, we might get 1 per square kilometer per year. So it's very unlikely we're going to get many of these really high energy particles, but these are the ones we need in order to trace back to the origin of where these things come from. But there are experiments on the ground, and some of them have been rather productive. For instance, relatively recently, we heard about this event. This was the second most energetic particle ever detected to hit the Earth. It's called the Amaterasu event. It was detected from an array of particle detectors in Utah. It was reported in Astronomy Picture of the Day a few months ago, based on data that was taken a while ago and then recently analyzed. The Amaterasu event, you can see this artist's impression indicating that part of the shower was caught by the array, from which they've got enough data to backtrack and work out just how energetic this particle was and to backtrack its direction. Before I pass on from this slide, let me just make it clear. The Amaterasu event should not be confused with the tiramisu event, which is what they had at the party afterwards when they realized they'd discovered such an energetic particle. So the idea is, well, if it's really energetic, it shouldn't be deflected by magnetic fields, so we should be able to figure out where it came from. So they did that with this, and they traced back in the sky where this particle came from, this really, really, really energetic particle. And what they found was, when they traced the direction back, they found it pointed to, pause for dramatic effect, nothing. There was no supernova they could identify. There was no supermassive black hole that seemed to be in the direction that this thing was pointing. So we need to do more research. Is it because it's not a supernova or a supermassive black hole that's producing these really energetic particles? Or is it because, despite what we think, the magnetic fields out there somewhere are deflecting this particle, even at these enormous energies? We still don't know. The more energetic a particle, the closer it's moving to the speed of light. So how fast are these really high energy particles traveling? The Amaterasu event was the second most energetic. The most energetic recording so far is called the oh my god particle, because when the scientists first saw it, they genuinely could not believe that any particle could have that much energy. When they converted the energy into how fast it was going, they found as a percentage of the speed of light, its speed must have been 99.9999999. We're not done yet. 999, still not done yet. 999, nearly there. 995% the speed of light. It is very difficult to get your head around just how close to the speed of light that is, but that must be what its speed was to give it the energy that they detected in these cosmic ray detectors. And my final slide is, let's try and just visualize what that actually means, because there's just too many nines there to get an idea. Let's imagine we had a race over 100,000 light years, and the race is between the most energetic cosmic ray that we've ever seen and a photon of light. And the racetrack is 100,000 light years. So roughly speaking, the sort of diameter of the galaxy. The light and the cosmic ray are going to start at exactly the same time, and they are going to run down this racetrack. Now, if we're talking about a vacuum, perfect vacuum, then of course the cosmic ray can't go faster than light. Of course, light must win the race. But the question is, when the light crosses the finishing line, how far behind it is the cosmic ray that's traveling close to the speed of light? After a journey of 100,000 light years, the cosmic ray will be behind the light by an amount equal to 5 millimeters after 100,000 light years. If you wanted that in terms of time, after a journey that lasts 100,000 years, give or take, what will be the time difference between the light crossing the finishing line and the cosmic ray crossing the finishing line? They will be within a nanosecond of each other after a race lasting 100,000 years. It'll actually be way smaller than a nanosecond. It will be only a few picoseconds, basically. So the bottom line is these cosmic rays are really, really, really energetic, or at least some of them are. So let me summarize, because I've talked for long enough, way long enough already. Cosmic ray particles are accelerated somewhere, somehow. We don't really know where, and we don't really know how. It is thought that supernova and supermassive black holes, the jets from supermassive black holes, are involved. They're probably sources, but we haven't got proof of that yet. We know that cosmic rays are deflected by magnetic fields, and we think that low-energy particles would have their paths completely scrambled by the magnetic fields. We hope that the higher-energy particles have a chance of pointing back to their genuine sources, but that seems to be problematic even there. We know that some particles make it past Earth's protective magnetic field. Our magnetic field stops some of the low-energy stuff, but the really high-energy stuff still gets through. What does get through hits the top of the atmosphere and generates an air shower of secondary particles. These secondary particles, quite a few of them, will make it to ground level. There will be muons, there will be electrons, there will be protons, and those secondary particles that make it to ground level will make clicks in Geiger counters and make tracks in cloud chambers. So the clicks we're listening to and the tracks that we were seeing earlier in the cloud chamber could be from supernova, could be from the jets of supermassive black holes, or perhaps something else. We don't understand how they get so much energy. So the clicks you're hearing, remember, each click signals the arrival of a cosmic ray particle that may have started its life somewhere else in the galaxy, or perhaps in a different galaxy altogether. You're listening to the cosmos. Thank you for listening.